I am Rudraishwarya Banerjee from San Diego State University and my advisor is Professor Satish K. Sharma. My presentation topic is a dual circular polarized wideband flat panel phased array antenna for Ka-band 6U CubeSat communication applications. Circular polarized electromagnetic waves are preferred for space-to-space and ground satellite communications. Cube satellites with 6 unit sizes require high-gain CP antenna systems to maintain the reliable communication link between lunar surface and ground terminal. So in this NASA-funded project, we have designed a dual circular polarized flat panel phased array antenna which works in Ka-band frequency range. And wideband 22 to 28 GHz 8x8 dual circularly polarized phased array antenna aperture comprised of sequentially rotated elements in each 2x2 subarray is designed. This array offers gain of 23 dBIC in broadside direction and beam scanning capability of ±50° with 3 dB gain drop and offers acceptable axial ratio over entire scan volume and over the entire bandwidth. Here, phase shifters from Anoki wave RFICs are employed for the beamforming network, which help us to accomplish the sequential rotation, or in other words, the phase required for sequentially rotated elements. And also, it provides the phase shift required for dual CP as well as beam scanning performances. This is the 8x8 array of the dual circular polarized radiating element along with the beamforming board layout, and this is the 2x2 sub array, and this is the magnified view of the 2x2 sub array, whereas this is the magnified view of single element of this sub array. So we can see, if we consider this is the first element, then we can see this element is 90° rotated with respect to this element, and this element is 180° rotated with respect to the first element, and this element is 270° rotated with respect to the first element. This is the sequential rotation, and this helps us to achieve better axial ratio. Here is the reflection coefficient and isolation between the two ports for this single element, and this is the active S parameter for the 8x8 array for the center element of the 8x8 array for broadside direction and different scan angles, and this is the radiation pattern of the broadside direction of this 8x8 array at 25 GHz. So here is the beamforming algorithm for circular polarization and beam scanning, and we have employed Anoki wave RFICs to execute this beamforming algorithm. And here is the scanning performance at 25 GHz in 50° plane, and here we have plotted the realized gain versus different scan angles as well as axial ratio versus different scan angles at three frequencies: 23.05 GHz, 25 GHz and 26.5 GHz. And from these two graphs we can see maximum broadside gain ranges from 21 to 23 dBIC over the entire bandwidth, and beam scans till ±45°, and axial ratio is below 3 dB over entire scan volume for entire bandwidth. So this 8x8 array aperture along with the PCB stack-up of the beamforming network is co-simulated with the power splitter outputs and chip outputs, and we found the performance of the antenna is still excellent when non-ideal chip performance are included in our analysis. The 8x8 antenna aperture along with the beamforming board is fabricated, and the full fabricated phased array antenna will be tested soon for radiation pattern in the Antenna and Microwave Laboratory of San Diego State University. Thank you for listening my presentation.